So let's discuss a little bit about muscular system. And on this recording, we'll just start with some of the basic concepts to get us oriented, and then we'll review the individual skeletal muscles that I really want you to know a little later. But I think it's a good place for us to talk first a little bit about different types of muscular tissues, their functions, and the microscopy. So if we think on a very large scale, muscles really, their function is to transfer energy, which in this case would be the ATP. So that's how the energy currency of the cells. And we transfer the chemical energy into mechanical energy. We're going to see that as, for example, as a movement or a force that we're producing. And what we're seeing in this picture is really those individual sugars that can then be converted to ATP at the mitochondria, and that then gives us the resources to perform that muscle action. If we think of the term muscles a little bit more, the term really comes from Latin language for little mouse. And I think that what that captures quite beautifully is really that microscopic nature of the structures that end up generating that movement. So although we see these large prominent skeletal muscles that we often end up studying in anatomy and physiology courses, really the story behind that happens on a microscopic level. We'll also end up seeing that all muscles share some terminology prefixes like myo and mice. They refer to muscle, whereas the term sacro is usually the prefix for flesh. And when we talk about muscle fibers, it's worthwhile to remember that we're talking about muscle cells. And this is because both skeletal and smooth muscle cells are elongated. So the contraction and shortening of the muscles is then explained by these microfilaments moving. And we'll discuss that a little bit more further in this presentation. I do want to take us though to the very basics. So first thing we're going to do is look at the three basic muscle types found in the body. And we're going to start with the skeletal muscles. That's going to be our focus for this chapter. We'll revisit the other muscle types later in relevant body systems that we'll review. But skeletal muscles are these big muscles that we think of when we're thinking of the movements of the body. They attach to the bones by tendons. And we'll end up seeing that we have few muscles in the facial area that also attach to the skin. But generally, these skeletal muscles, big muscles, attach to bones by tendons. If we look at an individual skeletal muscle cell, we'll end up seeing that it is fairly long, fairly large, cylindrical shaped cell. These skeletal muscles typically have multiple nuclei. As a result of the development, we have had multiple cells fusing together to form that final skeletal muscle cell that we're studying here. And we typically end up seeing that those nuclei are located at the edges of the cell. Another thing that's noteworthy is that we're going to see striations. So those are those stripes. And those stripes are really our actin and myosin filaments letting light through at some parts and not at other parts. Other thing to notice about skeletal muscles is that they are voluntary muscles. So they're the only muscle tissue under conscious control. So let's have a look next how skeletal muscle cells come together to form these tissues that we might study. And looking at the connective tissue wrappings of the skeletal muscle here, skeletal muscle cells are surrounded and bundled by connective tissue. And we're going to see endomusium, which encloses a single muscle fiber, perimusium, which wraps around a fascicle of a muscle fibers, or known also as a bundles of muscle fibers, epimusium, which covers the entire skeletal muscle, and finally fascia on the outside of the epimusium. It is worthwhile to notice here that epimusium turns into connective tissue attachment to the bone, and those were, of course, our tendons. So tendons are mostly collagen fiber, often cross joined, and they are tough and small in size. So I could, for example, highlight that muscles don't have to be located per se on the site where they act on. And I think hand muscles are particularly good example. Many of them are located actually further away. Otherwise, our hand would be very, very chunky. So it is those fibers that can run, those tendons that can run and cause those movements by the muscles that are actually located outside of where the actual movement takes place. And while all muscle types produce movement, our focus will be on the skeletal muscle, as I mentioned. I will, however, mention also our cardiac muscle tissue, which is found only in the walls of the heart. These are branching cells that have a lot of connections with other cardiac muscle cells. So they really, by working together, form this unified contraction that's characteristic for the heart. We're also going to be seeing intercalated discs, which pass materials and messages across from one cardiac cell to another. So again, we accomplish that unified contraction. Typically on cardiac muscle cells, we see one central nucleus, and we also will notice that there's striations present. And these striations are actin and myosin fibers letting in some light through the area, as not as much light is passed at other areas. We'll end up seeing that cardiac muscle cells are involuntary, so the heartbeat is automatic. It does adjust based on the needs of the body, and also with the cardiac muscle cell that they contract at the steady rate that is set by the pacemaker. We'll get to talk all about that good stuff when we get to the cardiovascular system and look at the heart. Let's finish off our basic muscle types in the body by looking at the smooth muscle found mainly at the walls of hollow visceral organs such as stomach, urinary bladder, respiratory passages, but also at the blood vessel walls. The shape of smooth muscle cells is very much changeable. It can change a lot, kind of resemble a spindle at the rest. Again, we see one central nucleus and we do not see striations. These are involuntary types of cells. There's no conscious control a lot of time over the smooth muscle, and they do produce slow and sustained contractions as well. So next thing that I wanted to do was to discuss briefly about the four functions of muscular tissue. And we often think of this first function, the production of the movement that helps our body to move in the world around us. And again, even though all muscle types do produce movement, but the following three that I'm going to highlight here at the functions are especially important to skeletal muscles. So the next one that I wanted to talk briefly about is going to be that skeletal muscle tissues help us to maintain posture and body position. So there's a lot of muscle activity taking place, even if we don't physically cause a significant large observable move. I think yoga is particularly good example of that. While body parts in that are not moving in a large range or rapidly, these muscles still are working very hard, so it provides us a good workout in that sense. We also end up seeing that muscles help us to stabilize joints. So just standing still is constant realignment and readjustment that's going on. So there's a lot of muscle activity even in that setting. Finally, I wanted to mention about the muscles and muscle tissue functions, about their role in generating heat. So we end up seeing that whenever we convert energy from one form to another, some of it does get lost, and typically that's lost as a heat. But this can also be intentional, as it is, for example, when we get shivers during cold time, we're trying to produce that heat. Sometimes it's kind of more of a byproduct. When we're exercising hard, we get warmer. We have to be at the gym where we have AC. But that can be a positive thing that we capitalize on. There are also many other functions. What muscles do is far more complex than what we often think of initially. And while I let you look at those examples on your own, I'll mention the smallest muscle that I can think of in the body, which is, of course, our erector pili muscle. We discussed that when we discussed the chapter about the skin and how erector pili were responsible for lifting the hairs when we got the goosebumps. Well, let's move ahead and have a look of a little bit of histology of the skeletal muscle, and we're going to start on the smaller scale. So sarcomeres are these fundamental units of muscle contraction, and they're made of protein filaments. So what we're seeing on the screen as a sarcolemma is a specialized membrane around this. And we also see myofilaments. These are filaments that sarcomeres are made of. And there's different kinds of, especially the actin and myosin are the two that we're going to be focusing on. So on this picture, again, you see myofibril, these long organelles inside the muscle cells. And let's zoom in a little bit into this myofibril that we're seeing here. So here we see one sarcomere, the contractile unit of muscle fiber, and let's look at the organization of the sarcomere in more detail. And we can see this striped pattern that gave whether muscle cell was striated, such as skeletal and cardiac muscle cells, or not striated, such as smooth muscles. So what we're seeing here is really the myofilaments, what sarcomeres are made of, and we're going to see actin, which are the thin filaments, and myosin, which are the thick filaments. And we'll explore those a little bit more. And please notice that where we have entirely only thick filaments, that's going to appear as a dark band on that microscopy. We saw those on those striated muscles. And where there's entirely thin filaments, that's going to be a light band. So that's the light portion of what we saw with a microscope. So that gives us that striated appearance. And I have here a microscopy image very close of the skeletal muscle that allows you really to see those dark and light bands. Now let's look at a little more diagrammatic representation of the skeletal muscle sarcomere as actin and myosin filaments, and they're color-coded there on the picture. And we can see that these are present even when we look at with the electron microscopy method. So we see these small projections in addition. I often describe them to my students in a layman's terms as little legs coming out from the myosin. Their real name really, I think, ought to be cross bridges. So they are responsible for linking with actin filaments. And this helps actin and myosin to slide past each other. And let's look at this a little bit more. So what we see here is when the muscle contracts, the actin and myosin filaments slide past each other. So on this picture, what we're seeing on the left-hand side is a relaxed muscle, and on the right-hand side, a contracted muscle. You'll see how it shortens, and it shortens again because these actin and myosin filaments are sliding past each other. I think that we already discussed about those little legs that help actin and myosin to slide past each other. I do want to mention at this point that if we were to look at the process on a chemical level, one of the important elements that we'll see is calcium. And calcium is something to keep on mind later because we're going to see that in many physiological processes on a chemical level. But this is especially true, the calcium's role in muscle activity. And when we're talking about calcium, there is one concept, we're not going to dwell on that, but I'm going to mention that. But I am going to give warning at this point if anyone feels really uncomfortable. I have a couple of pictures of people who have passed away here. We won't dwell on those a long time. But one of the concepts that we're going to see is that calcium kind of ends up locking those actin and myosin filaments together after the death when the rigor mortis step sets in. And this causes the muscles to stiffen very hard, in fact, so hard that the body can carry its own weight. The words rigor mortis really come from Latin, referring to the rigid death. So we're seeing on these individuals that the rigor mortis has set in. We use the timeline when rigor mortis sets in, when it passes, to figure out also the time of the death of an individual in those sorts of research or those sorts of analysis settings. So moving on from this, I do want to bring this back to the this microscopic anatomy back together with physiology, and let's look at a few different types of muscle contraction. So the first one that I want to talk about is our isotonic contraction, and then we're going to talk about isometric contraction. So isotonic contraction, what we're seeing happening here is that the myofilaments are able to slide past each other during the contraction, and as they're sliding past each other during the contraction, the muscle is shortening and the movement really takes place. And we can see many examples of this. This is how we see a lot of those large movements. I think knee bending. We do this, for example, when we lift weights or even when smiling. So that's kind of a familiar one for us. But let's unpack a little bit our isometric contractions. So in isometric contractions, although the muscle filaments are trying to slide past each other, the muscle is actually kind of locked, pitted into this against an immovable object. So as a result, when the tension will increase, but the muscle length really does not change, so the muscle does not get shorter. I think a good example of this would be if we take our palms and push them against each other in front of you. My muscles are very much working when I put more force into this, even though we're not seeing a change in the length of the muscles. So that would be a good example of isometric contraction in comparison to those isotonic contractions, where we saw the muscle shortening and the movement was very obvious. So that brings us to the end of the overview of muscle tissue. And I also want to talk a little bit about the skeletal muscle activity. And we're going to finish off, if we have time, talking a little bit about the naming of the skeletal muscles as well. So we're going to just keep ahead and we're going to start with golden rules that we should keep on mind when we're talking about the skeletal muscle activity. So to understand skeletal muscle activity, we need to look at these 5 golden rules that explain it. And here we have them, so let's unpack them a little bit. A first rule that I've mentioned there is that with a very few exceptions, all skeletal muscles actually end up crossing at least one joint. We're seeing that often that the muscles don't really attach to the same bone for start and end. They cross over 2 bones so that there's a joint in between. And other thing to notice is that typically the bulk, or if you want to call it the belly of the muscle, so the bulk of a skeletal muscle lies at the proximal to the joint that they're crossing. So a lot of muscles are closer to the proximal than distal portion when we focus on the what joint are they really crossing. We'll also see that all skeletal muscles have at least 2 attachments, the origin and the insertion. Obviously, there's going to be times when we're going to see more, but at least 2. We're also gonna want to be really, really careful to remember that skeletal muscles can only pull. They never push. And this is going to be an important concept for us as we think of the movements. We're also going to see that during isotonic contraction, the insertion moves towards the origin. The origin never moves. And I think that the reason why we really needed to know these 5 rules is that they allow us to understand the next section, where we'll be having a look of different types of movements. So let's unpack those a little bit more. So we're going to go through each of these body movements. I provided you here a list of all of them, but we're going to break it down, go one by one of these. But I wanted to provide a slide where you could see all of them at that kind of a bigger picture view. So let's start by talking about flexion. So flexion decreases the angle of the joint. And what we're seeing is that we're bringing 2 bones closer to each other. And an example, for example, would be bending hinge joints such as a knee or elbow, like I illustrated. We even see this at the ball and socket joints at the level of hip. I also extension. So extension is the opposite of flexion that we just saw. In extension, we're increasing the angle between two bones. So the straightening of the elbow would be a good example of that, same for the knee. What I've also highlighted on this is that we can sometimes do something that's known as hyperextension. So in this case, we're extending beyond 180 degrees. So I could do flexion, I could do extension, but I could also do hyperextension. I could go beyond that normal. These hyperextensions do come with the injury of risk sometimes. So we really kind of want to be mindful if we're hyperextending that it is safe to do so. I also wanted to show another picture of flexion and extension. I think that the neck is particularly good. Again, flexion, we're decreasing the angle. Extension, we're increasing the angle. And we could also hyperextend our neck, go beyond that 180 degrees. Then I wanted to talk about rotation. In rotation, we're seeing a movement of a bone around its longitudinal axis. And this is really common at the ball and socket joint. So one good example that I'm showing here is moving the atlas, the bone around the dens of axis. So we're creating this shaking no head movement. So that would be a good example of rotation. I also wanted to talk about abduction and adduction. Let's start with abduction. So we're moving a limb away from the midline. So think of abduction as taking away. I guess in popular culture, we see sometimes stories about alien abduction, someone taken away. Whereas adduction instead is the opposite of abduction. We're moving the limb towards the midline. So we're adding it to the body. If you focus on the three first letter, adduction for adding. Next movement that I wanted to mention is our circumduction. Circumduction is actually a combination of flexion, extension, abduction, adduction. So this is really common on ball and socket joints. And what we end up seeing in circumduction is that the proximal end of the bone is stationary and the distal end can move in a circle-like movement. So if you think of a range of movement, it's almost like an ice cream cone shaped range of movement. Next, let's talk a little bit about dorsiflexion. This is lifting the foot so that the superior surface approaches the shin towards the dorsum. So, for example, walking on heels would be a good example here, whereas plantar flexion refers pointing the toes away from the head. For example, walking on toes like a ballerina, if you wish. I've also wanted to mention inversion, so turning the sole of the foot medially, and inversion, turning the sole of the foot laterally. Let's talk a little bit here about supination. In supination, the forearm rotates laterally so that the palm faces now anteriorly. So now the radius and ulna are running parallel. I often use this as an example to my students that when your palms are up, it's almost like you're carrying a bowl of soup, and that would be a good example of supination. Pronation is the opposite movement, so radius and ulna cross each other like an X-shaped arrangement, and the palms are facing down. And of course, as you can remember from our first week of learning together, we saw that we can talk about pronation and supination not just in relation to the palms, but in relation to the entire body. And I don't think that this one was on your list, but I'm going to include it regardless. Opposition refers to moving the thumb to touch the tips of other fingers of the same hand. So really important for when we think of the evolutionary changes of the human and how that has allowed us a way to manipulate objects, for example. Now, let's look at next for general types of muscles. But before we do so, I do want to mention a few general notes to remind our thinking. So first of all, muscles can only pull as they contract. Remember, they did not push. And we also want to think of the fact that groups of muscles that produce opposite actions lie on opposite sides of a joint. So we would see, for example, when we study muscles of the forearm, flexors and extensors. So they're often on the opposite sides of each other. And there's going to be 4 types of muscles that we can categorize. The first one of those is going to be our prime movers. These are muscles with major responsibility for certain movements, and I've highlighted some examples below there. We're also going to see antagonists. These are muscles that oppose or reverse a prime mover. Then we have synergists. These are muscles that aid a prime mover in a movement or reduce undesirable movements. And finally, our fixators, specialized synergists that hold a bone still or stabilize the origin of a prime mover. So for the final part of the day, when we're learning muscles, I have a couple of tips for you to consider. We will focus on the first one, which is that we can get a lot of information about the muscle and what it does simply by looking at its name. And all of the other points that I've highlighted on this slide, we will cover later on. So when figuring out information from naming muscles, there's 7 things really that I think that we ought to look at. So first thing that we're going to look at is the location of the muscle. Muscles are often named after the bone they are associated with. For example, temporalis muscle lies and starts above the temporal bone. Shape of the muscle. The clue is often given in the name. So for example, deltoid muscle of our shoulder is very triangular in shape and coming from the Greek word for a triangle. The size of the muscle, sometimes many muscles of the same, we have many muscles of the same at the same area, and we differentiate those based on their size. So I think a good example would be we have gluteus maximus, medius, and minimus at the buttocks. So the size of the muscle is really the clue there. Or we could talk about muscles that are either longus or brevis, so long or short. We can also look at the fiber direction. So rectus tells us that these fibers are running straight. Transversus tells that they're in transverse angle, and oblique that they're in an oblique angle. And we'll unpack this in just a second. We can also look at the number of organs. So bi means 2, tri means 3. So for example, biceps brachii muscle has 2 ends that we're going to pay attention to. We can also look at the location of the muscle's origin and insertion. I think one of my favorites is sternocleidomastoid muscle. It tells the 3 points where it attaches at the sternum, clavicle, and mastoid process. And we can also look at the action of a muscle. We just revised these, so whether they're flexors, extensors, abductors, adductors, I think we did a good job with those. And finally, sometimes we see a combination of many of these. So for example, extensor carpi radialis longus muscle tells us that it extends rest at the radius and is long. And to finish off, I mentioned the fiber direction, so let's unpack that a little bit more. And we have most common patterns here on the screen, and we're going to start with the circular arrangement, which is the ring-like arrangement. We see that, for example, around the orbicularis oris muscle around the mouth. We can have also convergent fascicle arrangement. So this is a broad origin that then converges into one, and I think that pectoralis major is a really good example there. Fusiform muscles are spindle-shaped. They have parallel fibers that fuse into one, such as biceps brachii muscle. We have parallel fibers here. For example, sartorius muscle is a good example of that. And finally, we have pinnate muscles where the fibers attach to a central tendon. And this can be one belly, it can be 2, or it can be even more of the muscle bellies. And that really brings us to the end of this video. I know it's been a lot of information, but you always have a chance to pause and go back and revise. Until next video, thank you for joining. I'll see you then again. Bye.